topic. And so then let's invite all the panelist speakers today to the session. So I think most of speakers are still here. So maybe Cecilia, I think I need you to lead the discussion. And this is thank you for volunteering in the first place. This is very tough discussions to have, from embodied cognition to evolution to soft embodiment and the soft robotics and so on. So hand over to you, Cecilia.
Thank you. Thank you. It was an amazing session, actually. And as expected, we touched different, let's say, it's different forms of intelligence, what we mean by intelligence, from more embodied ones to more cognitive ones. But as I tried to introduce since the beginning, we have to find a way to put all the aspects together, because this is what happens in nature. They are not separated and segregated. So I would like to start with, let's say, the most material part and most mechanical part of intelligence that was mostly presented by Jun Shintake. So actually, with you, we saw intelligence already in the materials. The materials it's themselves, they are intelligent. The materials that you use. And then your fish, I mean, I think it's a very good, you asked this question at the end, but I think it is a very good example of embodied intelligence, because in your swimming movement, you use a lot of the interaction with the environment. So probably you didn't do specific experiments, but I'm sure that the control is quite simplified, and also the energy need is also reduced because of that. My question is actually, if with your work you can somehow estimate to what extent you are using embodied intelligence, even if that was not your specific target, but in the end, your robot probably uses embodied intelligence a lot to simplify control and to reduce energy needs. So what's your, let's say, your feeling about this from your experience with your swimming robots?
Clearly, there is benefit of embodied intelligence in our robot, and I think soft body can be excellent platform to observe and demonstrate the function of the intelligence, because when we have a soft body, it can react with external environment because it's soft. It's soft. If it is rigid, of course there should be some sort of reaction forces acting on the surface, but we have difficulty to observe like interaction in the end, because there should be almost no deformation and resulting thrust force in the case of underwater robots. And then yes, but I'm not so sure how we can quantify the function of this intelligence implemented in soft body. Even I'm sure that we are exploiting embodied intelligence for making efficient swimming.
So yeah, maybe more than just being soft, because sometimes in soft robotics there is a bit of misunderstanding that we must be soft, but in your specific case it's more the elasticity of the body.
Right.
And store energy and release energy for improving the swimming. So I would like to link this with Sylvester's talk, actually, because if we said that embodied intelligence helps reducing the control burden, I think this can be very helpful for you, because you have a human brain attached to the robot, to have prosthesis in your case. So you don't want to have a high control, let's say, workload, right? So to what extent you think you can use embodied intelligence in the prosthesis itself? So it's a combination of materials, of under actuation, I think, in the end, to reduce the control signals that are needed. And so it's probably simple to connect a human brain to that, right?
Thanks a lot. That's an extremely good point. I was thinking actually while you were discussing about it, is clearly a necessity. Now, if you start with the idea that you are going to take a bit of neural resources and reuse them, think about the extra limb, then clearly, but also for the prosthesis is the same. The amount of information you can decode from the brain or from wherever it's limited. This means that you really need some kind of help. It could be a classical shared control, or it could be even better, an embodied intelligence in the arm, for example, which can reduce the amount of information you need to extract. And this is crucial because the better is the starting point in terms of performance, the more the user, the patient, the final user will use it from the very beginning with the possibility of learning over time. And under actuation, as you said, is already an excellent example, yes. But we can do way more than this. In particular, I would say for the third arm, becomes really crucial to go for something more embodied in terms of intelligence of what we can do now. Because clearly, if you think about using respiration or we are using auricular muscles, you can extract information, but not with the same level of complexity.
How many signals, more or less, can you extract?
I mean, in principle, what we are doing right now is to use the two auricular muscles with respiration. And this seems to work, actually. Of course, so there are 2-3 degrees of freedom. More than this, it is possible, so you can add, but clearly will be more complicated for the user to start using it effectively. So I would say 2-3 degrees of freedom, that's something we can reasonably do, but then again becomes absolutely a necessity to have the arm helping us in some way.
There's hope, because the octopus arm is so complex and they only use 3 parameters from the brain to control it. So
Exactly. There's a perfect example. I totally agree. Thanks.
Okay, so David, you are talking about sort of higher level of intelligence, and actually I think that especially with your final picture, your figure at the end of your presentation, where you show that embodied cognition is actually at the intersection of body, brain, and environment. You probably answered my initial question at the start of the session, so how to put everything together. So, but let me better understand. So how and you also mentioned the ecological niche, which is also a very important concept in embodied intelligence. So let me better understand to what extent embodied cognition actually puts all the things together, but to what extent is it constrained into an ecological niche, or can go out of it and be effective in more niches or in a more complex environment?
Sure. So I mean, so the ideal of the research we're doing in soft robotics at the moment is to hit that. So what I call true EC, and again, that's just my definition, is the the controller and the body and the environment are all given like equal weighting, and a lot of what we're trying to do at the moment is bring the environment away from being like a passive arbiter of fitness and use it to actively improve the learning process of the agent.
Right.
So you could consider it an environment that itself is actuated and is trying to discriminate the behavior of the agent, right? So that's some of what we're doing right now. And that's also like the one of the disambiguations between that and the engineering. The engineering is more, or like the field robotics approach rather, is more like we have this environment and, you know, if the robot survives and we can maintain it, then we're good. To more directly answer your question, I think the nice thing about evolutionary approaches to EC is the evolutionary paradigm itself is very general, right? You can consider like open-ended evolutionary systems, but even just your standard genetic algorithm can generate completely different organisms, let's say, depending on the environment you put it in. So I think you can generate specific niche-based behaviors just by tweaking your objective function, or by exposing the agent to those niches. Right? So if you want an agent that works over 10 niches, you just assess it across the 10 or give it a fitness metric that allows it to average across the 10 or so on. So you can do it like that with evolution. It can work. So my experience is that it often does not work depending on what you're trying to do. So like open-ended approaches, obviously they're good for some things, but they fall down in others, right? And the standard GA one doesn't scale. Yeah.
That's actually the criticism of evolution, or the warnings for taking inspiration from evolution, because it's very much related to a specific environment, and also it's an incremental improvement. So it's not the optimal solution, but actually it is a solution and it is an effective solution. So I'm asking for me if we are supposed to take questions from the audience at some point. So I don't want to take all the time over. I see one in the chat.
Yeah, Julie, it's up to you. Go ahead.
Okay, so we may try with this one, which is for all speakers actually. So could more intelligent organisms depend more or less on embodiment? I'm not sure I understand exactly the question. Could more intelligent depend more or less on embodiment? I understand. It's a good question. And is the regulation?
I think it can. It can. If this agent or robot has like high level of control algorithm that recognize embodiment intelligence by itself. So I think Sylvester said embodiment intelligence could be a sort of under actuation, but in the end, I think we have a way to quantify the computation functionality of this kind of intelligence. And then if we can do that, of course, we could have more intelligent organisms in the end. That's my opinion. Thank you.
Thank you. Yeah, I don't know who asked this
So the
question.
thing is that now we are treating embodiment intelligence as kind of a passive function, but actually in the end we can exploit activity. That's what I think.
Yeah, that's a good point. That's a good point. And yeah, probably it's also a way to go out of the ecological niche and to be able to, to be having more than one ecological niche if we, find this active exploration. Okay, I'm checking if there are more questions from the audience. I don't see, so we can go on discussing this topic. So And as I said, I'm very much puzzled by how putting together higher forms of intelligence with the more mechanical one that we usually relate to embodied intelligence. Maybe a very simple way would be to actually have a sort of a higher level, cognitive level, that can take some decision to which of, let's assume that our system has some embodied intelligence mechanism, maybe limited to some ecological niches. So can we just add a sort of decisional level on top of this that can at least switch between different more embodied behaviors? And if so, how can we build it? So can we build it by learning? Can we build it by evolution, as David was proposing a while ago? So who wants to elaborate on this point? Or can it be a new best doing that?
I could have a go. So I mean, so there's a load of work done by people like Sam Friedman and Josh Bongard on like environmental mediation, and I think you could do a part of that. So like, what they were doing something relatively simple but quite neat with you know, the voxel-based soft robots, and whenever the robot interacted with the environment, the material changed its properties, right? So you ended up having a more rigid contact with the environment. You could transfer more force. All this happened autonomously. So it was not programmed. You could think about doing something like that with complexity. So like you could have a notion of morphological complexity where obviously we'd want to keep it as simple as possible, because ultimately we have to build this thing and get this orchestrated behavior out. But you could imagine like a system that does that. It's probably better to do that as a generic mechanism rather than think about sort of trying to do machine learning for compartmentalizing different behaviors. So like you can do that, but in a lot of cases you know what the answer was anyway, so you might as well just implement a structure that makes sense and allow the bits that are required to be adaptive. That's one way to approach it.
Okay. And Sylvester, do you want to add anything? I know you have to leave a little earlier.
Yes,
so
I would say that in our case, I don't know whether you can hear me.
Yes.
Because it's a bit chopped. In our case, what we try to do in neuroprosthetics is to find a way to have the human being and the neurotechnology, whatever, co-evolving over time. And in general, to have embodiment for prosthesis, for example, what you want to have is the patient getting a bit more control when it's possible. So if you want the embodied intelligence, the shared control is crucial to start, but over time, you can relax it a bit if necessary, and if the subject is able to cope with the increased complexity of the control. So you can have different approaches, more flexible, combining, let's say, the intelligence of the device, the intelligence of the person, and the interface in between. And that's one of, really of the hot topics in neuroprosthetics, how to start combining the two things in a flexible and more useful way for the patient. So that's really something we are now starting working on in the field more and more. It's really a very interesting question scientifically.
Okay, thanks a lot. Thanks a lot for this additional view. Your perspective is, of course, a bit different from ours. We always think of autonomous robots, so that's very helpful. Another let me go to another point that I already made, the point of energy. Because this is very much related, I think, to embodied intelligence and maybe to the real motivation for that in nature, because energy consumption is very critical in nature. So we already discussed a little bit with June, but maybe David, you also may add. You showed that you use the soft materials for improved locomotion. So I assume that if you use the soft materials, the elasticity of material, the interaction with the terrain, and all those kind of mechanisms, in the end, you have a big reduction of energy consumption. If we compare all that to a classical humanoid robot with rigid links and rigid joints, also actuated by motors. So did you ever consider that? Is it a part of your research, or did you just observe something like that?
Yeah, great question. So yes, we do notice this typically when we employ soft systems. The weird thing is that they're kind of integrated into rigid systems. So it's like sort of articulated soft, but we do see in most cases we see that we're saving energy overall. And not only that, but we are also much more adaptive and resilient. So with the leg example, for example, you know, the sort of ground reaction forces we're seeing, that's the primary saving that we're making. You know, we're using just dynamics or motors, but we're extending the life of that robot, potentially reducing the maintenance costs, allowing it to go on to, so we consider it also in terms of accessibility. Like we want these robots to actually go out into these really nasty environments and do something useful. And we see soft systems as a gateway to allowing us to do that in a really nice sort of principled way. In terms of energy savings, the priority of that really depends on where what system we're deploying it on. So for example, if we were to add the system to a spot robot, for example, the batteries on that thing can go for hours anyway. So it's not necessarily a huge priority. However, if we were to consider a soft system on its own, that would be much more of a priority for us then. We'd also be looking at, you know, ways of doing energy harvesting from the motion it's generating. We'd be looking at flexi solar, things like that. You know, how do we store energy? Because like, so the really tricky thing from a battery perspective as well is you essentially need two types of batteries in most cases. So you need one that can hold the energy for a long time, but you also need one that can provide spikes of energy very quickly. And those are typically competing requirements.
Yeah, actually, that should be our final goal, energy scavenging. If we reduce the energy need, we can explore more solutions in that direction. Actually, especially if we consider autonomous robots and so on. Actually, I was discussing with a colleague here in electrical engineering working on batteries and power system, and he told me something that is probably straightforward. I had never thought about it. If we consider the energy we need for those devices, and if we consider the rate at which they are increasing in numbers, if you just put some numbers, you realize that the energy we have on the planet is not enough. So we really have to go for different solutions. And in robotics, we definitely, and with soft robotics, we have a great opportunity for doing that. If we use body intelligence, we reduce the energy need, and then we can go for energy scavenging and this kind of solutions. There was a question that I hadn't seen, sorry, for June, actually, which says that real fish have some intelligence to understand the environment, for instance, the water flow, and maybe changing their behavior. So would it be possible to implement such an intelligence into your fish robot? It's probably related to what we were discussing before, like integrating body intelligence with some decisional level. of intelligence.
Oh, yeah, it's not gonna be intelligence, but I think I had same question from some people attending this conference, asking me if the efficiency or performance of underwater robots can be improved by like sensor skin employing pressure sensors. And I think the answer is yes, because by recognizing pressure distribution on the body, I'm sure that the robot can find kind of optimal swimming behavior or actuation way to improve the performance. That's for sure. So yes, in the end, I think we need some sort of sensorized skin on the interface between the body and the environment. And also, just let me talk on the previous question, not question, but the point. Right now, we are trying to implement energy harvesting functionality in soft actuators and robots. And because now we see that, especially those electrically controlled robots, the efficiency is really low. It's pretty low. Very low. so now we are making multifunctional soft actuators that have multiple functions such as actuation, sensing, and energy harvesting. By implementing those multifunctional components, I'm sure that we will have high performance, intelligent soft robots.
Yeah, we can reduce computation a little bit, but actuators are still, energy hungry. Okay, I think